In this video, we're going to talk about optical instruments, which is a topic that you need in the IBSL test, option G. Let's start by just checking with your familiarization of some of the basic qualitative topics about lenses that we've learned thus far. What we're going to do is we're going to ask you about 6 different quick questions that I want you to try and answer within 10 seconds from when the slide first appears on the screen. I'll quickly read it, and then you'll have about 5 more seconds to make your best guess before the answer flashes. So in which of the following locations would you place an object to get an image the exact same size as the object? And the answer is at 2 times the focal length away from the lens. Will give you an object that is exact same size, an image that's the exact same size, and even in the exact same place on the other side of the lens, just upside down. I don't know if this is going to work. Blah, 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 blah. Where would you place an object to get a virtual image? This is a really key one to have memorized, that you need to put the object anywhere between the focal length and the lens. Inside this region will give you a virtual image. Everywhere else will give you a real image. How can you tell when you use the thin lens equations whether your image is a virtual one or not? The answer is that the image distance v will be a negative value if it's a virtual image, or a positive value if it's a real image. How can you tell using the thin lens equations whether your image is upright? The answer is that the height of the image will be positive when it's upright, and it's negative when it's upside down. Now the last question, using the thin lens equations, how can you know if your image is smaller than the original object? This one has a plain and clear answer, which is just, hey, HI should be smaller than HO. But there's another way as well, and I was hoping you may have thought of this, and that is that the magnification will be a value less than 1. This is important that we recognize any number less than 1, that means the image is smaller. If it's bigger than 1, that means the image is taller than the object. All right, so we've covered a couple of basics. These are things that we should already have after everything we've done so far with lenses. We should qualitatively be able to answer those questions pretty quickly. Now what we're going to do is we're going to look at different lenses and see what happens when lenses basically go bad. And how do you solve those problems? These are questions you should be able to answer on a test on option G, and they're just usually just like explain-like questions. So you got to know this information. One of the terms they want you to know, or one of the ways that a lens can be made incorrectly, is with what we call a spherical aberration. An aberration is simply an abnormality or something that's wrong. So spherical aberration has to do with the actual shape of the lens itself. This curvature here is supposed to be the right shape, and if you grind it and make the curve the incorrect shape, then it's not going to actually have one clear focal point. So you need to know what spherical aberration is. We just explained it. And it's when the shape of the lens is wrong. And you need to explain what that's going to do to the actual image, and how do you know it has spherical aberration? Well, 1, it doesn't have a clear focal point. 2, a spherical aberration can make it so that an object looks fuzzy or distorted. A simple window, like if you looked at you're standing in a window with a box and like lines like this, the window actually might look kind of weird, where it's like curved in at each side instead of being a nice simple box. It could be skewed, or it could just be blurry. how do you fix spherical lenses? Or, sorry, spherical aberration? Well, usually the problem occurs on the outside edges of the lens itself. Okay, this is usually, it's easier to grind it on the middle. It's harder to get the right curvature on the edges. So this is usually where the problem is. And so the easiest way to fix spherical aberration is to somehow get rid of the light from the outside, because that's what's mucking it all up anyways. So you can simply either just slice the lens smaller, or you can actually put something here and something here to actually cover up these rays so it doesn't actually go and form your image. Now the disadvantage to that is that you're now going to have a much dimmer image. You'll still have the full image, but it'll be dimmer. Not as much light is going through, but at least it won't be distorted. And this is one of the things that they had to do, for example, to fix the Hubble telescope. They had spherical aberration when they sent it up there originally, and had some problems, and so they had to go up there and kind of make some goofy convex lens to fix it. That's the other thing that you could do, right? They made a convex lens that was mostly on the outside but not on the inside, and it was almost like a donut, and then it unbends these light rays so that they meet more towards the center. All right, another way that lenses can go bad, and it's not really they're going bad, but because pretty much all lenses will do this, is that they can have what we call chromatic aberration. Basically, all lenses do this. There's no way around it because this is just a phenomena of dispersion, which we've talked about. The fact that shorter wavelengths of light, like blue or violet, tend to bend more or refract more than longer wavelengths like red, means that the blue will have a different focal length than the red when you send white light through a lens. This can be quite problematic. You might have even remembered this on our activity when we shined the 5 rays in with our lens slab, and it was a little bit more red on one side and a little bit more blue on the other. This is chromatic aberration. All lenses are going to do it. There's no way around it, but there are ways to fix it, right? You can do something to counteract the effect of chromatic aberration. And so in high-end cameras, they'll do this. A lot of times we'll just deal with what it is because it's so minor, who really cares? But in high-end cameras, they have ways to fix it so that you actually get a nice, clear picture. How do you actually go about fixing it? Well, you have to fix it by getting another lens, basically, to unbend the light. It has to be a different material. And you have to find the right amount of material and the right shape of the lens. You got to get it all right to basically unbend the blue more than you unbend the red, and have it come together all into one spot. It would basically, in short, look something like this. Maybe you have a lens that's made out of crown glass, and if left unchecked, these two, the red line would meet at a different spot than the blue line if they were left to go straight. But you might make something out of a different material like flint glass. It's now a concave lens, which tries to unbend the light a little bit. It unbends blue more, right, because of it has a higher index of refraction, right? It'll bend more because it's a lower or a shorter wavelength. And so it will unbend more than the red, and we get the right combo, the right shape, the right distance apart, and we can, boom, get them to actually merge at the same location. And so we can solve this by doing a bunch of fancy trickery with different types of materials and shapes of lenses and just balance it all right. Now that we've talked about aberrations with lenses, and by the way, those topics are really some things you're just going to write down on a note card and review right before a test. It's not something that you need to use for problem solving, so it's something you need to memorize. Let's get down to the crux of the actual presentation today, which is that of optical instruments. Now really, we want to get at what the purpose of optical instruments are, usually to make something look larger. We want to ask ourselves, how do you actually do that, make something look larger? Well, I have a couple questions that might get at that question here. And in the past, we've talked about making an image that's taller, but that's not the only way to make it look larger. Case in point, if we have a 6-foot tall person, can we hide that 6-foot tall person behind a 5-foot tall wall? Now you might say to yourself, of course I can, that's pretty silly. All I have to do is take the person and have them duck down. But there's another way too, right? Instead, you can take that 6-foot person where they were visible before and move them backwards. And then we say, hey, now all of a sudden there is no line of sight towards him. Well, can you hide a 50-foot wide wall behind a 2-foot wide person? What if we put the person in front of the wall? Well, that's possible too. Just move the person, imagine, if you will, moving the person so close to the eyes that the eyes are just basically right in that person's belly. Well, you're going to see nothing now but belly. This is a thing we call angular magnification. That belly is not wider than 50 feet, but it looks really big because it's just so close to the face. Let's talk a little bit more about angular magnification. If you, let's say, took your hands out, and you could try this right now. Take your hands out and put them straight out in front of you, and then you slowly move your hands out to the sides, wiggling your fingers. And as you wiggle your fingers, you're looking straight forward. Don't look at your hands, just look straight forward. But keep on moving your hands very slowly outwards until you can no longer see your fingers in your peripheral vision. Once you can no longer see, if you then look around and take a look at where your hands are, you're going to see a certain angle between those two hands. That angle is usually around 100, just under 180 degrees, maybe 170 degrees or 160 degrees. So if your vision has so many degrees of angle that you can see, for example, this picture here, we might stick them close enough to someone's eye so that the tip of his toe is really at the bottom of someone's vision. You can do this with your pencil too. Pick it up and move it closer and closer to your eye, standing straight vertically upwards until the bottom of the pencil is at the bottom of your vision and the top of the pencil, like this person, is at the top of this person's vision. And you can't see anything past that, right? You get any closer and all of a sudden you can't see the eraser of the pencil or the head of the person. And then you say, okay, well, that person's taking up all 160 degrees of this person's vision. Well, if I move this person backwards, well, now going from his head to his toes, he's only taking up maybe like a 50-degree angle within his vision. Now, the person has 160 degrees of vision to play with, but he's only taking up 50 of those degrees, of those 160 degrees that he has. In fact, we like to use the word subtends a lot. We would say that person only subtends or takes up 50 degrees within your vision, okay? And it's only using 50 degrees of those, of your original total 160 or whatever you have. Every person's slightly different, depending on where your eyes are set on your head. So even though the person's the same height, he hasn't changed at all, he looks bigger, right? This is like that thing where you take your fingers and you you put your thumb over your index finger over your thumb, and you leave a little gap, and you look at someone's head through the gap, and you pinch your fingers up and down, and you're saying, and you put it close to your eye, right? And you're saying, I'm squishing his head, I'm squishing his head. You're just making your fingers look big. You take up a lot of angle of whatever angles you have relative to the size of that person's head. All right, so there are then two types of magnification, and you got to keep them straight. There is what we call linear magnification and angular magnification. Now, in your IB data booklet, on the last page of our IB data booklet, option G, you'll see both of these equations. The little m is for linear magnification, right? And that's just a simple ratio of heights, height of the image over height of the object. Angular magnification is capital M, and it is equal to the ratio of the angles that are subtended, right? So if you take the object originally, and you say, normally it takes up or subtends this angle with my vision in this case, best case scenario, and then I'd say, at best using my optical instrument, the image subtends this other angle, right? And so you'd say, whatever angle, if I can get the angle to be bigger, it doesn't matter if the image is taller or not. If it's bigger, maybe it just brought the image closer. As long as it's bigger, takes up more angle, it's going to appear bigger, and you're going to see more detail on the object, just like bringing an object closer. So in a minute, we're going to start talking about optical instruments, and there are three particular ones that you need to know about. We're going to be talking about the magnifying glass, the telescope, and the compound microscope. But before we do, really we should just know that angular magnification is really what these optical instruments are all about. We want things to look bigger, not necessarily have the image be bigger. We just need it to look bigger. Whether the image gets bigger or not, that's all we care about. Now, there's a couple other random things you should know. For example, with some of these optical instruments, like telescopes and compound microscopes, there are two lenses. So we're going to talk about these two different lenses, and we have names for them. And just so that you're aware, we'll call one the objective lens because it goes near the object, and one we'll call the eyepiece because it goes near the eye. So before we actually look at it, there's a couple of other random things that you need to know about your vision itself. And that is that your vision, you can only see things so close. Like we said, hey, look, you want to make it something look extra big, bring it close to your face. But if you take your hand and put it like right next in front of your eye, sure, it looks really big, but you can't really see any details, right? Your hand's blurry. Your physical eye only has so much ability to focus. It only has a certain range of focus. Okay, and with someone with 20/20 vision, there's a standard distance that you should have. Everybody, it's different. Right, as your eyes go bad, those distances will get worse. But the near point and the far point are what we call the closest and the farthest points you can see clearly without straining your eye. So how close can an object be? Well, just take your finger and put it out far, and you put your hand outstretched, and then slowly move your finger closer and closer and closer to your eyes, and then just stop when you feel like if I bring it any closer, I'm really working hard to see it. And if you measure that distance, that point wherever your finger is, that's called the near point. And that distance between your eye and wherever the near point is usually about 25 centimeters. Okay. And they give that number the letter D. I'm not sure why, but they use capital D. And if you look in your yellow packet or in your IB data booklet on option G, in the equations, sometimes you'll see a capital D. That capital D is the near point. And for a standard human being, on average, with 20/20 vision, it's around 25 centimeters. So we're just going to assume that is 25 centimeters for everybody. I know that's ridiculous, but that's what we're going to do to make our lives a little bit simpler. So D, please write down somewhere, capital D in your equation sheet, option G, capital D is 25. It's always 25 centimeters, right? Or 0.25 meters. Now, the farthest your eye can see, well, that's actually pretty easy. Think of the farthest object you can look at clearly without really straining your eye. I mean, you can see a mountain in the background, right? That's not hard. Can you see farther than that? Can you see the moon? Can you see stars? Well, heck, stars are really far, aren't they? Your eyes can actually see all the way out to infinity, or just psychotically far objects like stars, right? Without a problem. It's not very hard. In fact, your eyes are relaxed. That is the most relaxed they're going to get when you're looking at objects that are super, super far away. This is called the far point. And we say for a standard human with 20/20 vision, it should be at infinity. A couple of random points you should memorize. All right, so let's take a look at our three specific types of optical instruments. We're going to start with the simplest one, the magnifying glass. Now, something you should know. A lot of people don't use magnifying glasses correctly. Now, the person who is in this picture, this little cartoon character, is using the magnifying glass correctly. So as we're talking about using a magnifying glass, I want you to think of your eye right next to the magnifying glass. Okay? Now, if your eye is literally right next to that magnifying glass and you want to look at an image and you want to see that image clearly, where might you put the object so that you can get an image that is both bigger, we'd prefer right side up, but it might be upside down. Sometimes optical instruments do that. And we would prefer it to be, close to our eye if we want it to be big, right? And we'd rather have it be in front of our eye. Now, I know that last one is a silly question. Do you want it behind or in front of your eye? Well, it's kind of a silly question, right? Of course, I want it in front of my eye. But you think about it, a lot of images appear over here on this side of the lens, right? Which is actually behind your eye. So this last question is actually key. If I want to see the object clearly, or the image clearly, I need the image to appear over here on the same side of the lens as the object is, okay, in front of my eye, because my eye's right next to the lens. That means there's only one of these 5 locations that will really give me all of these, especially that last point. And that is, I got to have the object at 5 between the focal point and the lens. Let's go ahead and now learn how to calculate the angular magnification for a magnifying glass in an ideal scenario. In order to do that, we're going to look at the angle an object subtends with your vision without the aid of a magnifying glass, just by itself. Let's say we're looking at an ant or something. We want to see what angle that ant takes up in our vision at the best scenario. And then we're going to look at the angle the ant's image would take up with our vision when we use a magnifying glass. And we'll divide the two. We're going to use this equation. Then we're going to derive an equation that's in your yellow packet. And to be perfectly honest, the derivation is not really that important and hard to follow sometimes. So I'll try my best to explain it as best I can. And I'm going to take the time to do that simply because they want you to know the derivation in your... that's one of the requirements for the objectives of this course. So I'm going to go over it once briefly. But for the most part, look, you just need to know the equations and how to use them. For the most part, the odds that they'll ask you for a derivation question is very low. But we'll do our best. Here we go. So we say, okay, with the object itself, this angle here, theta, like if this is the ant, this is how tall the ant is, right? And when I'm holding no lens, when I'm holding the ant 25 centimeters away from my eye, the tangent of theta, right, this angle here, theta O, is equal to the height of the actual object, we're calling it an ant, divided by the 25 centimeters, right? So we're going to use this equation here in a little bit. And we say, you know what, tangent of really small angles, because we're looking at small objects, they're actually pretty close when you use radians to the actual angle itself. So we're going to make a substitution. I hate all these dumb substitutions, but this is what we do because it's close enough, we just don't care. Tangent of the angle theta O is pretty much just kind of theta O. It's really close when we're using radians. So we're just going to kind of get rid of the middleman and say theta O, the angle the object subtends with your vision, is equal to the height of the object divided by 25. All right, so we're going to now do something similar with the image, okay? So what we're going to do is we're going to stick our eye right next to the lens, okay? And here's a lens, and we're going to put the object, remember, this is the original object, the ant, and we're going to put it between, here's the focal point and the lens. We're going to put it somewhere in this general region so that it makes a virtual image. Now, where would we want the virtual image to be? Well, I'm actually going to move this ant, the object, back and forth until I get that virtual image to be as close to my eye as possible with me being able to still see it clearly. If you try this with a magnifying glass and you take an ant and you move it really close, you can't see the ant because the image is too close to your eye and you can't see it. You move the ant farther back and, well, you can still see it, but it's just kind of blurry. You move it over here, there's no way you're going to see it because now you got real images and the images behind your eye. So there's kind of like a sweet spot, a general area where you can kind of see things, and then there's a sweet spot where it's the biggest possible because the image just happens to be the closest it can be to your eye, 25 centimeters, and yet you can still see it. Now, the actual object itself, though, right, is a lot closer than 25 centimeters, but the image, what we're actually looking at, or what we think we're looking at, is 25 centimeters away from our eye. So we can do the same thing. We can draw this angle here, and we can do this whole thing with the tangent of the angle of that subtends the image, right, is equal to hi over 25, and we can do the same substitution, theta I, right? And then we can say, okay, well, then this here equals this equals also equals ho over u, right? So this hi, the height of the image, divided by this distance, 25, but it also equals the height of the original object divided by u, the object distance, right? You can see that this line that goes to the object, that's really close to my eye, closer than 25, is the same, excuse me, it's the same that goes to the image itself. So we can say, that's useful. We can then simplify, get rid of the middleman. Now that we've got some equations for theta I and theta O, we can do a little algebra voodoo and kind of combine some things together and get a finalized equation. Again, if you don't follow this, don't worry about it too much. So I'm going to take my thin lens equation, 1 over the image distance plus 1 over the object distance equals 1 over the focal length. And I'm going to take it and I'm going to plug in the information that I have. So at best, I have my image at the near point, 25. It's just going to be 25. Or in our equations, sometimes we just put capital D, right? And we're going to plug in whatever information we got. And we're putting in a negative, right, because it's a virtual image. And we can rearrange this, just do a little bit of algebra, right? Move the 25 over to both sides. In order to add the fractions, I need to make a common denominator, right, and add my things together, and I get the following fraction. And then I can finally take my equation for angular magnification, theta I over theta O, and I can say, theta I we saw earlier was equal to HO over U, and theta O is equal to HO over 25. I can plug things in, and we simplify to M is equal to 25 over U, okay, the object distance. Then we say, okay, but what is U? Well, we just a slide before, we were looking at what U is with the thin lens equation, and we made this equation over here. 1 over U is equal to 25 plus F over 25 times F, right? So we can do a quick substitution, put that in there, right? And then all of a sudden we have 25 on the top, and that just cancels the 25 on the bottom, and then we're left with simply this. And then we can do, again, one little final last step to kind of simplify some things, and we get 25 over F plus 1 is equal to the angular magnification. This is the biggest magnification you can ever get, and a lot of times instead of 25, they actually just put capital D up here, and you just have to remember capital D is always 25 centimeters or 0.25 meters. So this equation can be found in your option G in the IB data booklet, except, like I said, I believe it says capital D. So the problem is that not everybody actually uses a magnifying glass correctly. I mean, I know I never did. And just a quick search on the internet for people using magnifying glasses, little kids, and I found this, a couple of cute pictures, and you can see they're totally not using it right. These kids are not holding it up to their eye and moving the object really close between the focal point and the lens, getting an image that is 25 centimeters away from their eye. No. They're just holding the magnifying glass up to the object. And you can actually get an object to be magnified this way, and it still is very big. But it's not the biggest you can possibly get. The other way was better. Okay, so we'll take a look and we'll derive what's the biggest you can make an image look like if you're holding it incorrectly, meaning towards the actual object itself, because this is a common way people also use a magnifying glass. So what you do is, in order to get this to be the biggest image possible, is that when you hold it away from your eye, you hold the object actually at the focal point, or really, really close to the focal point. This will make the the image freakishly large and freakishly far away, which is the biggest the image is ever going to get. And so what you can do is, by doing that, you get this thing to be very large, and the object distance then becomes F. Okay, so earlier we said that theta O is, let's see if I can get this right, theta I is equal to H over U, and theta O is equal to H over 25. These still work, except that the U will now just be simply F instead of whatever equation we derived last time. So we're going to plug these things in, do a quick little algebra voodoo, rearrange, and we get, angular magnification, when you use the magnifying glass incorrectly, meaning holding the magnifying glass near the object and away from your eye, is 25 over F. This is different than the last equation. So here are our two equations as written in the IB data booklet. M is equal to D over F, and M is equal to D over F plus 1. This one is clearly smaller than the exact same thing plus 1, right? This is the one that you get when you use a magnifying glass properly, where you hold it next to your eye, and the object is between the focal point and the lens, and you get an image that's at your near point. This equation you use when someone is using the magnifying glass incorrectly, well, not the best way, and holding the glass near the object itself, where the object is at the focal point, and the image is at infinity. You have to memorize that D is 25 centimeters. If your focal length is in meters, then that's 0.25 meters, right? You've got to remember that. And another annoying thing, so you got to know when to use each equation. They're both for magnifying glasses. Another really, really annoying thing is that you've got to remember these are actually angular magnifications, and yet they put a little lowercase m there, which we stated earlier was linear magnification. So be warned, this is still angular magnification, and it infuriates me that they put a cap or a lowercase m. It should have been a capitalized M. All right, so here are a couple of key notes about magnifying glasses. Number one, you need to know how to draw a ray diagram for a magnifying glass. Specifically, the first one, right, where the object is between the image or the focal point and the lens. We've already done this. We've already practiced this. Can you just simply draw a regular ray diagram when the object is between the focal point and the lens? Okay, you should be able to do that. Follow your ray rules and just draw it. So if you don't have one of these sketched out, you should sketch out the ray diagram, a ray diagram for this in your fill-in notes. A couple of key facts that you should also be aware of. Right, the object is placed between the focal point and the lens. That's the thing about the diagram that you need to remember, right? That's where we put it when we draw the diagram. Another thing you should know is that your eye is assumed to be close to the lens, right? Just like it's shown in this picture. We should also keep in mind that the image will be a virtual upright image, and ideally 25 centimeters away from the lens, which is where our eye is, right? Or in other words, we call that the near point. And then one last point. Just joking. Apparently there was no other points. Okay, so now let's talk about lens combinations. How do you handle when you have more than one lens? We need to know this because our next two instruments, telescopes and microscopes, both have lens combinations, an eyepiece and an objective lens. So how do you handle when there's more than one lens? It's actually really easy. All you do is you just treat one lens at a time. So look at the first lens by itself, okay? And just draw your regular ray diagram, okay, and figure out where the image is. Great. Now, what you're going to do is you're going to take that first image, and that first image becomes the new object for the next lens. And so you just pretend like that first lens wasn't there and draw a new ray diagram where the first image is this object, and you draw another one, and then you say, you can put it all together, right, and you get the whole ray diagram, right? It just creates one image, first image, and a final image. And the total magnification would be whatever magnification you have here. Looks like it got, I don't know, maybe a little bit smaller, like maybe 0.8 magnification, and then it looks like it got bigger here, so maybe twice as big too. And so the total magnification for this lens setup is the product of those two magnifications. You can just multiply them together. And that's how we use multiple lenses. So the idea is to use both lenses in such a way that it actually makes it bigger both times. You can see in this random example, this did not really make it bigger both times. We did not really take advantage of truly the lens capacity the capacity of the lenses to actually make images look bigger. And that's what we're going to try and do with both telescopes and microscopes. Let's start with a compound microscope. So ideally, when you're using a compound microscope, and I'm pretty sure you guys have all used a microscope before, so this is actually really going from memory, right? When you used a compound microscope, did you get an image that was bigger or smaller? You got one that was bigger, right? Do you remember, was that image, was it right side up or was it upside down? Now, not everybody remembers, but if you recall back in biology, when you were looking in microscopes and moving things around, whenever you moved that slide up, the actual image went down. So everything was actually upside down. It was backwards. So unlike a magnifying glass, you get an image that is upside down. It's inverted. And ideally, we'd like the image close to our eye, and we would like it in front of our face, right? So that we can actually see it instead of behind our face. So where do we actually put the original object in order to get an image that takes advantage of both lenses and still has an image that's back here? Well, that means if it's over here, that means the final image I'm probably going to want to be a virtual image. Okay, so I want the first image to land somewhere between the focal point and the lens, so the final image I get a virtual image, something that I can actually see in front of my face. If I got a real image and then a real image, that's going to be a problem, and the image is going to be behind my eye. So I want a virtual image at the end, so I'm going to need a real image that appears somewhere in this general area. Okay, so we place the object on the close to the focal point, but in front of the focal point, somewhere around this region. And on your fill-in notes, I want you to sketch an object somewhere in that general region, somewhere like I've drawn, and I want you to practice sketching the ray diagram. So sketch the ray diagram, find your first image, and then sketch it from the next one to find your final image. Now you'll know if you did it right. You're really just guessing where this object should be, but you place the object in the right spot if your first image, it has to, absolute has to, fall between the focal point and the eyepiece of the for the microscope. So if you did it right, when you draw your three-ray rules, right, parallel through the focal point, through the center, no bend, and then through the focal point, and then parallel, you will get a first image that is ideally between the eyepiece, the focal point of the eyepiece, and the eyepiece lens itself. Then from this, right, we can draw, this will become our new object, and we can draw our own, or another ray diagram, and right through the center, parallel through the focal point, and then the last one is looking like it came from, remember, coming from this focal point. This line is lined up with the focal point, but it goes towards the lens. And then when it hits this, notice it doesn't actually hit the lens, but who cares, just pretend the lens is really tall. When it actually hits where the lens would have been, it goes parallel, right? And then I can trace those three rays back, and I can find where they meet, and where they meet is the final image. And you'll notice when I put it all together that each time it gets bigger and bigger, and it stays in the very end inverted and virtual is the final image. So take a moment and try and draw this ray diagram for yourself on your own notes, because this is something you need to be able to produce. Sometimes there are test questions where it just says draw the ray diagram for a compound microscope. It's like 3 or 4 points. So we're going to go over the ray diagram for a compound microscope and talk about some of the key aspects of it that you really should have down or understand about that ray diagram. Now, really what they want you to do is they just want you to magically memorize the ray diagrams for both compound microscope, telescope, and a magnifying glass. Magnifying glass is nice and easy. If there's just one lens, you just draw a ray diagram. But the other ones, it's a little bit more complicated, so there's more aspects to it. And if you haven't drawn it right in your notes, you need to have this somewhere in your notes, this diagram, so you can practice it, memorize it. But if you don't have, you're a little afraid you didn't draw it right, keep in mind you can get a copy of this diagram. You can just go on into your Orange Review textbook in option G, just look at the contents, table of contents, and you can look and see they have a nice diagram there for it. But we're going to emphasize some of the key points. If you ever had to reproduce part of it, here are some of the key points that they're going to be looking for when you do that. Number 1, you should always recognize that the focal length of the objective lens is always smaller than the focal length of the eyepiece. That's really critical. That's the only way to actually get the magnification that you're looking for, is to have the focal length originally of the objective lens smaller than the eyepiece, as shown here. Another thing is that the object needs to be placed between FO, that's the focal length of the objective lens, and 2 times the focal length of the objective lens. Let's take a look. So here is FO, right, focal length of the objective lens. You can notice that's much shorter than FE, the focal length of the eyepiece, right? And so we say, okay, focal point, 2 times the focal point away from the lens, looks like around here. And you'll notice, hey, look, that object fell between those 2 points, right here and here. And the reason is so that way it creates a larger, the first image will be a larger image and a real one in this range, right? That was so critical. And if you had this object too far back, let's say at 2 times the focal length, well, then your fish image is only going to be equal to the same size. And what's the point of that? Any farther past 2 times, and it'll be smaller, and that's no good. So it has to land in this region in order to use a compound microscope correctly. Another key thing, and we talked about this a lot already, is that then the first image needs to appear exactly between the focal length of the eyepiece and the eyepiece itself. So this range over here is where the first image has to appear. And then finally, the final image will ideally be a virtual inverted image that's hopefully somewhat close to your eye in order for it to be as big as possible in the most in a reasonable way. All right, telescopes. Before we move on to telescopes, let me just say one more thing about microscopes. You'll notice there was no equation for microscopes that we covered. That's because there is no equation for microscopes in your IB data booklet, and they don't expect you to calculate any angular magnifications for that. However, they will have one for telescopes. They have 2 for magnifying glasses used in different scenarios, and they have 1 for telescopes. Let's go over it. So ideally, with telescopes, we want an image, again, that's bigger. Preferably, we'd like something that's right set up. I don't know if you've used telescopes before, but they are also backwards, so we'll get one that's upside down. Preferably, we'd like something that's close to our eye, right? If we can look at it right, it'd be bigger if it's closer to our eye. So, let's check some familiarization. Remember, what kind of, where should you really place the object in order to get an image to focus at the focal point itself? Do you remember this? The answer was objects that are really, really far away, right? Parallel light focuses at the focal point. So none of these work. Really, an object that's at infinity or really far away, that's the only kind of object you're really going to get that's going to focus at make an image at the focal point. Another thing that you should know is the exact opposite, right? Where should you place an object to get an image that's really far away or infinitely far away? The answer for this is the exact opposite, right? Just like the other one. You want it, if the object is at the focal point, then you get an image at infinity. This is qualitatively, we've gone over this in the past. And this is useful to know when we deal with telescopes because we're usually looking at objects that are, like stars, very far away. So let's look at a refracting telescope, the ray diagram for one. And we call it a refracting telescope because the light bends when it goes, or refracts, when it goes through a lens. And this is different than what we call reflecting telescopes, which actually uses curved mirrors. All right, so a refracting telescope. So when we look at light that's from a star, right, it is really, really far away, approximately at infinity. So we have light coming in that is actually parallel. And so this light that comes in that's parallel, and I want you to sketch this on your diagram for your fill-in notes. Light that comes in that's parallel, right, it comes in at an angle from the top of the star and goes in, and it forms an image right at, just like we discussed, the focal point itself, right? It all focuses at the focal point. Now, you'll notice that one of the key things about this this telescope is that you can't see it because now the thing's in the way, but the first image, but the focal length of the objective lens is actually right on top of the focal length of the eyepiece, and this is what we call, this is what we say when the telescope is in quote-unquote normal adjustment. Okay, so normal adjustment is when you move those lenses back and forth such that they fall, those 2 focal points fall right on top of each other. Okay, so if it makes an image at the objective lens's focal length, then it will make a new image for the eyepiece that is also really far away or at infinity. Okay, so the light then leaves the eyepiece's focal length, goes through the new lens, and then comes out looking parallel. So when you're looking at the object, it still actually looks like it's really, really far away. So one might stop and say, wait a second, how does this actually make the object look bigger then? Well, if you take a look at this, the angle that the original object is subtending with your vision, which we'll assume like the star is, the base of the star is on the principal axis, right? And the top of the star is over here. These are clearly over-exaggerated angles. This angle right here is smaller than the new angle that is made with the new image, okay? This one fact alone is really what causes a telescope to allow the image to appear to our eyes bigger. It will subtend a greater angular, it will take up more angle, subtend a greater angle in our vision. So let's sketch the ray diagram for a telescope and write down a couple of key facts, right? So a couple of things that I hope you've noticed at this point that is different than the last one is, one, the focal length of the objective lens is this time longer than the eyepiece, which is opposite for a microscope. So the focal length of the objective lens is larger than the focal length of the eyepiece. Without this, it would not be magnified, it'd actually be smaller. Another key fact is that the light comes in parallel, right? And meets at actually, another key thing is that there are two focal points, they have a mutual focal point where they're right on top of each other, and this is called normal adjustment, right? So when the telescope is in normal adjustment, the focal points for both lenses are placed right on top of each other. And another one is that the light coming from far away is parallel coming in. So that's something you got to sketch, that parallel light coming in. And then you say, and where you don't really need to worry about drawing the correct rays because you know where the image is going to be. That first image then is going to appear right on the focal point of the objective lens, which is the mutual focal point for the eyepiece, right? So the first image is formed on the focal plane for their mutual, both the eyepiece and the objective lens. And then the final image, right? The light will come out going parallel. And so the final image will be out at infinity as well. And it'll also be virtual and inverted and really far away. Like I said earlier, we have an equation for telescopes, and we have two equations for magnifying glasses, but none for microscopes. Let's derive quickly the equation for angular magnification for a telescope in normal adjustment. So again, angular magnification is theta I over theta O. We can see from our diagram, this over here is the angle the object subtends with our vision. This over here is the angle our image subtends with our vision. And so we're really going to just measure those two angles and then calculate the ratio. So we see, okay, so this angle here, right, is the same as this angle here. So we've got a quick little triangle here where the height of the object is over here, and the focal length of the objective lens is over here. So the tangent of this, right, we just drop tangent just like we have done before, is equal to HI over FO. And then we've got a similar triangle over here, right? This angle here is the same as this angle over here. And we've got a triangle. And we just say, so for theta I, H over FE is theta I. And then we can just plug in and rearrange and simplify, and we get the angular magnification. Luckily, they actually use capital M this time. For a telescope is FO over FE. And I just need to remember, so focal length of the objective lens divided by focal length of the eyepiece. And I just have to remember that this is only used for telescopes.